Hello everyone. Tonight's lesson will be on waves of light. We're on our fourth section of Chapter 2. We're looking at light emitted from the sun and as it reaches our planet. We'll be discussing UVA, UVB, and UVC radiation, all in connection with our atmosphere and the ozone layer. Some of the light we can actually see in what's called the visible spectrum, but many components of the electromagnetic spectrum are invisible to our eye. We describe light by color, but along with that comes a numerical value that corresponds to its wavelength. Let's take a peek at light in terms of its energy. Light is indeed a form of energy, and it travels in a wave fashion. When I look at a wave traveling, let's call this an axis, and I look at the, what's that say? Keep it, don't ask me again. Let's keep the idea of wavelength going, where I look at the distance from the crest to crest, or I can look at it from trough to trough. The length measured in a nanometer, I'm going to write that word so we can hear it and see it at the same time. A nanometer is 10 to the negative 9th meters. 10 to the negative 9th meters. It's a very small unit because the distance from the top of one wave to the next is a very small distance, so we'll use a small unit called a nanometer. Compare the wavelength of a red light to the wavelength of the blue light. Notice that the distance from the top of this wave to the next, the crest to crest, is a smaller distance. It has a shorter wavelength. A longer wavelength has lower energy. The higher wavelength has, the shorter wavelength has higher energy. Wavelength is written with a symbol called lambda. Wavelength is written with the symbol called lambda. Frequency is called nu, and really what you see is kind of a V for a Greek symbol. So the frequency, the symbol nu, and the wavelength, the symbol lambda. Let's discuss the term frequency, the number of waves passing a fixed point per second. So let's suppose this is a fixed point on our axes. The number of waves passing through that fixed point is significantly more when I have a shorter wavelength as I compare this fixed point and the number of waves that would pass through it in every second. Longer wavelengths have shorter frequencies. Shorter wavelengths have higher frequencies. We see that inverse relationship. The shorter wavelength, higher frequency, is telling me this is a higher energy wave. Here we have low energy, a long wavelength, and a very low frequency. Frequency is measured in waves per second, or simply per seconds. Notice that you can see that written as 1 over seconds, or sometimes you see that written seconds to the negative 1. And I've also seen them called hertz, which is a physics term, a unit of measure for frequency, a hertz, Hz. You'll often hear it called a per second. When we consider the electromagnetic spectrum, and that's what we're looking at, all the different wavelengths and different energies associated with different types of energy called gamma rays, X-rays, UV is ultraviolet electromagnetic energy. Here's the visible spectrum at about 10 to the negative 9th nanometers, and we start to see the rainbow of color coming out. We have IR, which is infrared radiation, like a heat lamp. We have microwaves, a longer wavelength, and radio waves. About 10 squared, 100 meters is a radio wave, so very, very tall, height of a skyscraper. Shorter wavelengths, high frequency. We're looking at high energy of a gamma ray. X-rays, of course, we see the person put on some lead protection and they're going to be around an X-ray. UV is about 10 to the negative 8 and so forth. So here we have very high energy, and here we have very low energy. Alrighty, so compare that to the rainbow of colors here, where we have blues and violets and reds and oranges and kind of greens in the middle. Maybe this Roy G. Biv sounds familiar. Red, orange, yellow, green, indigo, blue, or violet, if you will. Roy G. Biv. So we're looking at the relationship where blue or violet colored light is of higher energy, shorter wavelength, and red near radio, that's how I remember the two R's, red light is near radio waves. It's a longer wavelength and thus a lower energy. So Roy G. Biv describes the wavelengths, telling us a lot of information about energy. Short lambda, short wavelengths include UV, which is ultraviolet, X-rays, and gamma rays. Longer wavelengths include the infrared, some radio waves, and so forth. The electromagnetic spectrum allows us insight into the energy of a certain wave. And the wave is what we're looking for, especially in the atmosphere. If we have a very penetrating wavelength like UVC, ultraviolet C radiation, we want to protect ourselves from that, and so forth. So the reason we care about wavelengths is because in the atmosphere the sun is releasing these waves, and when they reach the earth we either have to protect ourselves or the environment from these harmful rays. So we're looking at how much energy each type of radiation possesses. Energy is said to be quantized. It exists in discrete steps like a staircase. So if I consider a staircase and I'm climbing up some stairs, I can place my foot here, here, or here. Very discrete levels. It is said to be quantized. If I compare that to just a straight ramp, if you will, there's an infinite number of places I could step on with my foot and up, increase as I go up the ramp. This is a quantized, let me write that word, this is quantized energy, very discrete steps. In light energy, these discrete steps are known as photons. Photons of energy, little packets or bundles of energy that are emitted with a certain wavelength and a certain frequency. Now in physics, we learn about an equation where energy can be calculated by a specific wave by knowing its frequency. Nu is the frequency. Remember that little Greek symbol? Nu is the frequency, lambda is the wavelength, frequency is kind of a squiggly V, and lambda is an upside down Y. So this is frequency. Planck's constant is indeed just that. It's a constant. It's a number that doesn't change. So if I have very high frequency, a wave is passing through a specific point per second at a quick rate, it's a very high energy. If I have a wavelength that's very long, so I have a small frequency, it's not passing through a specific point with a very high rate, I have a very low energy. We see this inverse relationship between wavelength and energy, or a direct relationship between frequency and energy. When I think about C equal lambda nu, let me back that slide up and write this out. C equal lambda nu, well, this will be in the next slide, but just kind of showing that variable there. C is what we call the speed of light, and it is also a constant. Now maybe back in high school days you remember some physical science. Speed of light is measured in meters per second. I can't get that written there. So a meter per second. 3.0 times 10 to the 8th meters per second is our speed of light. And so let me just clean that spot up. The speed of light is 3.0 times 10 to the 8th meters per second. Lambda is a wavelength. We'll learn that when we do some of these calculations, it will be in a meter, and the frequency we learned is in a per second. A meter per second is the unit on our speed of light. meters per second. Wavelength over frequency. So what have we learned? As the wavelength increases, light is less energetic. If I have a long wavelength that's a very low energy, it is not very frequent. If I have a short wavelength that's very high energy, I have a very fast frequency. That wave is passing through this particular point very quickly. The rate is fast, it's a high frequency, very energetic, short wavelength. If I have a long wavelength, a very low frequency, it's not passing through this point with any increased speed. This could perhaps represent red wavelength. The red would be a very long, it says about 700 nanometers. This could represent blue energy in terms of a shorter wavelength, approximately 400. This would be representative of an energetic wave, such as the blue or violet wavelength. Wavelengths are measured in nanometers, which is a 10 to the negative 9th meter. So here we understand that wavelength and frequency are related to the speed of light. The speed of light is a constant, so if the wavelength goes up, frequency must go down, so that when they're multiplied, they come out with the same number, 3 times 10 to the 8th meters per second. Energy of a specific wavelength is using Planck's constant, 6.63 times 10 to the negative 34 joules per second. Now, joules is the metric system of energy. We have heat energy measured in joules. So the joule unit times a second. A joules times a second is Planck's constant unit. Energy is measured in joules. If I take E equal Planck's constant mu, Planck's constant has a unit of a joule times a second, and frequency is in a per second. You can see how those units would cancel when they're multiplied, and we come up with joules of energy, the unit here. How many joules of energy does a certain radiation possess? Energy and frequency are directly related. High frequency, high energy. Let's review some things we know. We know the definition of a wavelength, the distance between two crests of an electromagnetic wave. We know the definition of a frequency is a rate at which a wave will oscillate through a specific point on an axis. So with this definition review, our wavelength from crest to crest or trough to trough, the distance between two crests, and the frequency, how many waves will pass through a specific point every second, the rate at which a wave oscillates. There's another word, and it's called amplitude. And amplitude measures, and I'll just maybe draw something here. If I have a high amplitude, I have a wave with a very high distance here, very long distance between the axes and the top of the crest. And if you compare that perhaps to something with a shorter amplitude, you could see, I'm trying to create a next wave. This amplitude is much shorter than the distance for this wave with a larger amplitude. Oh, that didn't come out. Amplitude. And my screen cuts right there. So amplitude is what I'm trying to write there. Now I say all that, but what we're doing with this question is looking at conversions. So let's go back and remember our nano unit, and we'll set this up by saying I'm given a meter and I want to get to a nanometer. So I have 0.0083 meters. And I think about a conversion where I want over given, I want a nano from a meter. And I know that a nanometer and a meter are related by 9 units. Meter is the larger unit, so I know it's going to take 10 to the 9th smaller units to make one larger unit. This is one way of hitting it, and perhaps it just depends on your preference. You may certainly consider this. 1 nanometer is 1 times 10 to the negative 9th meters. I bet we get the same answer no matter how you hit. So on the first point, the 0083 times 1E9, that's 830000. That's 1, 2, 3, 4, 5 zeros on my screen. Did you get the same? 83, 1, 2, 3, 4, 5. If I take point 0083 and divide by 1E negative 9, that's scientific notation on my calculator, we'll get the same answer. Point 0083 divided by 1E negative 9, and my screen gives me exactly the same thing. It gives me 8, 3, and 5 zeros. So you can tackle this conversion either direction and end up the same way. I learned it at always putting the 1 next to the larger unit and tell me how many places on the metric number line separate them. There's 9 spaces for the nano unit. But this is also a fair equivalency. 1 nanometer is the same as saying 10 to the negative 9th meters. It really doesn't matter which conversion you use, you'll get the same answer. It's a preference by you, the learner. Here's some more vocabulary off of your sapling. Which one of these has the longest wavelength? Well, if you were to measure the distance from crest to crest or trough to trough in each of these waves, which one would give you the longest distance? And clearly we all agree, letter B. I notice greatest frequency and greatest energy. They're the same question, aren't they? The greatest energy has the greatest frequency. So if I select a point, who's giving me the greatest number of waves oscillating through a specific point per second? And clearly that looks like choice C, the shortest wavelength. And what about the amplitude? Who has the shortest or lowest amplitude? And again, just eyeballing, it looks like the distance from the axes to the top of the crest in graph A is the shortest distance. B looks a little higher than A, C looks a little higher than A. A is the lowest amplitude. Here you're being asked to just compare X-rays and radio waves. X-rays are very high energy, very penetrating, very high energy. So an X-ray is the greatest of the energies. Because it has a very high energy, it's a very penetrating ray, it is because it has a great frequency. I would consider X-rays, remember these are very high energy rays. By the time you get to radio, they're like 100 meters from one crest to the next. They have a longest wavelength. Short wavelength, high frequency, high energy. Remember that we saw a diagram where we had Roy G. Biv. And I always remember R's are near each other. This is radio waves, very long wavelengths, very low energy. And V is the violet, and it's near the very high energy like X-rays and gamma rays. So the longer the wavelength, the lower the energy. Who's closest to these long wavelengths would be the orange. And therefore, when I see greater frequency and greater energy, those two are the same exact question. Those are nearer the penetrating rays like X-rays and gamma rays. Those would be the blue light or violet. Blue or violet light has greater energy. lots of sapling practice together. What will happen if the energy increases? If the energy increases, let's suppose I have, let's say, this wavelength, and all of a sudden the energy increases. That means I have now created a wave that looks like this. Did the wavelength increase? No, it actually shortened. The wavelength will decrease. A shorter wavelength is higher energy. What will happen if the wavelength increases? So now we're just looking at the opposite picture. If the wavelength increases, the distance from trough to trough is increasing, the energy goes down. The energy decreases because the frequency also decreased. You're doing a great job with these, with the concepts of energy and how it's related to wavelength and frequency. So now let's put it in perspective, put it back into the conditions we're referring to with the sun. Now the sun emits energy, and it does so at a specific wavelength. We're getting bombarded with all of this variety of wavelengths of energy. Some of it we can see, most of it we cannot. How does this story relate to ozone, the topic of our chapter? Well, if the sun is bombarding the earth with all of these countless photons, indivisible little packets of energy, it's the atmosphere and the living things that have to absorb the photons. The infrared radiation warms the Earth's surface, including all of the water, the oceans, the Great Lakes where I'm from, and so forth. But if we absorb too much energy, we start to see cell tissue damage. For instance, the retinas of our eyes could become damaged if we have too much exposure to high-powered radiation. The cells of our retinas, with the rods and the cones, are tuned into specific wavelengths, and those are into the negative, 9th nanometers. That particular wavelength where we see Roy G. Biv happen to be the visible spectrum. This is where we can see energy. We understand there's a lot of it we can't see. The ultraviolet region is energetic enough to cause displacement of electrons from neutral molecules, causing radicals. And that's of importance to us because if we get bombarded with so much UV radiation, ultraviolet radiation, it can cause genetic mutations, skin cancer, or other types of cancers as well. We need protection from the UV light. Now remember the spectrum. We had Roy G. Biv. This is the visible spectrum. Here we have IR, infrared, like a heat lamp warming your hamburger at McDonald's. But over here we have the UV spectrum, ultraviolet, so it comes after the violet. The ultraviolet region is where this energy is reaching the Earth, but it has the potential to cause damage. We don't see it, but it's energetic enough to cause genetic defects. How do we go about protecting ourselves from the UV radiation? And that's the ozone story. It's the oxygen-ozone screen that's protecting us from 3 varieties of ultraviolet radiation: UVA, UVB, and UVC radiation. UVA lies closest to the violet region of visible light. Therefore, it's the lowest energy. Remember on our spectrum, Roy G. Biv? Then we have here the ultraviolet spectrum. Ultraviolet will have A, closest to the violet color, B is in the middle, and C is closest to X-rays, the more penetrating radiation. So obviously UVC is a very high energy, right next to the X-ray region of the electromagnetic spectrum. Now, here's the good news. UVC is of the highest energy, almost as much energy as an X-ray, but it is completely absorbed in the upper atmosphere and never reaches the ground. Both oxygen and ozone, both of these molecules work to absorb the light in this particular wavelength. Oxygen and ozone, and we'll look at the chemistry of how, absorb UVC preventing it from ever reaching the ground. How important is the ozone layer? It's preventing mutations from this high energy from ever reaching the ground. UVA is of low energy, reaches the ground, no problem. UVB is filtered. Let's see how. Here's the same diagram kind of presented from your text. We have the UVA, longest wavelength, lowest energy. UVB, right in the tweens, we have 280 to 320 nanometers. Higher energy than A, but lower energy than B. And look at UVC, 200 to 280 nanometers. That's a very short wavelength, a very high energy. UVA is the least damaging and reaches the Earth's surface in greatest amount. We put on suntan lotion to protect ourselves from UVA radiation. UVB, more damaging than A because it's of higher energy, but not as damaging as B. Ozone works to absorb B. Here's UVC radiation right next to an X-ray on our electromagnetic spectrum. It is the most damaging, but it is not a problem because it's completely absorbed by oxygen and ozone. Think of it this way. UVA comes straight through. UVB is blocked by ozone. UVC is blocked by ozone and oxygen. That's supposed to be a UVC is blocked by both. UVA is not blocked. It comes through, but it's a very low energy. The low energy right next to a violet color. But by the time we get to UVC, it's so energetic, right next to an X-ray, we have two molecules that work in unison to protect it from ever reaching the ground. And the ozone layer protects us from UVB. Let's digest that, and this is a sapling question. Here it says ozone, which is O3, and oxygen, or O2, and they're molecules found in the stratosphere, and their job is to absorb UV light emitted from the sun, protecting us from harmful radiation. That UV light is absorbed by the molecules based on the amount of energy and their wavelength. Based on the chemistry of the ozone layer, select all that are false. The amount of energy associated with UVB is weaker than that of UVC, primarily absorbed by ozone, breaking the bonds in the molecule. That's true. That was right off the previous slide. UVC is the highest energy, breaking double bonds in ozone and molecules. That's true because UVC is absorbed both by oxygen and ozone. The oxygen-oxygen double bond is stronger in ozone and absorbs UV light in shorter wavelengths. The oxygen-oxygen double bond in O2 is stronger than in ozone and absorbs UV light in shorter wavelengths. So I'm going to remind you yet that is true because look, oxygen is only working in the very strong UVC range. It's a stronger bond and therefore able to tackle that high energy bond. The double bond in ozone is stronger than the double bond in oxygen and requires more energy from UV light to break the bond. That is the exact opposite of what we just determined to be true here. UVA has the longest wavelength, highest energy, and is most harmful. That is not true. We determined UVC to be the most harmful. And we can continue, but you get the idea. I'm not going to do every one of your homeworks, but we're just looking at who has the lowest energy, who has the highest energy. Of course, the lowest energy we know to be UVA because it has the longest wavelength. The highest energy is UVC because it has the shortest wavelength. The UV radiation that's absorbed by oxygen, well, we made ourselves a little grid. The oxygen, the O2, is absorbing the UVC and only UVC radiation. So here is absorbing UVC. What's being absorbed by ozone? Well, again, if we refer to our diagram, ozone is doing both the B and the C ultraviolet radiation. And so here we would have both B and C for ozone. Ozone plays a very important role in absorbing high energy and damaging UV radiation in the stratosphere before it can ever harm any life on Earth's surface. Damaging UVB radiation, ranging in the wavelength of 280 to 320 nanometers, can be absorbed by ozone. Now that's a long-winded question for a conversion. We want to convert 301 nanometers to meters. That's it. That's all it's really asking me to do. I want the nanometer to cancel, and I want to land with a meter. I know that there are 1 times 10 to the -9th meters in every 1 nanometer, or it's just a preference of how you like to set up your conversions. I would say that we could have 1 meter being equivalent, and again there's 9 units. It takes 10 to the 9th nanometers to equate to 1 meter. There's 9 places different. You will get the same answer when you hit that in either direction. And you're going to have the same type of problem here. You're converting from meters to micrometers. Ozone can absorb the higher energy by damaging UVC radiation. Convert the UVC wavelength of 2.54 times 10 to the -7 meters to a micrometer. And the symbol for micro is that squiggly U. And again, depending on how well we remember our metric system, micro is 10 to the -6th on our metric scale. So I would have 10 to the -6th meters equating to 1 micrometer. 10 to the -6 meters is 1 micrometer. And I can convert that out and land at a micrometer. Meters have canceled when I divide there. And I'll let you hit that for your sapling. We're understanding the importance of ozone as protecting us from this UV radiation. Oxygen molecules are more easily broken, and ozone plays an important protective role. Let's take a peek at the chemistry that's occurring through this process. Here's oxygen. It's O double bond O with 2 lone pairs. Molecular oxygen's Lewis dot structure. The UV ultraviolet photon is greater than 20, so that's 2 O's, so that's, I'm sorry, not 20, 2 oxygen atoms. If a photon of energy hits the double bond and it's of energy greater than a certain threshold, it can break the bond. So lambda is a wavelength. The longer the wavelength, the lower the energy. So if the wavelength is smaller than 242 nanometers, this bond will break. Here's ozone. It exhibits resonance. We have O double bond O, single bond O. When I say resonance, it's because that structure could also be drawn not by flipping the molecule, but by having the single bond in the opposite direction. And the term resonance, we actually said it's a delocalization of the electron density, so it's equal distance from the central oxygen to either of the other oxygens. It's resonance. R-E-S-O-N-A-N-C-E, resonance structure. So here we have ozone, and if it is broken, it needs energy of at least 320 nanometers. It's a longer wavelength, less energy. It takes more energy to break the double bond of oxygen than the double bond in the ozone due to the resonance structure. It's the tweener length of a single double bond. So here's the cycle, and the cycle is known as the Chapman cycle. Let's talk through this diagram and getting an idea of how oxygen and how ozone work to protect us from UV radiation. And that's what we're looking at here. We're getting hit by UV radiation from the sun. If the UV radiation is of higher energy, a wavelength of at least 242 or less, the oxygen molecule will break apart into oxygen atoms, atomic oxygen. So instead of being O double bond O, that's a molecule of O2, they're two single oxygen atoms, O and O. These oxygen atoms feed into this cycle. The oxygen atom can react with the molecular oxygen to give us ozone. Remember, this occurs in high forms. Let's say in LA, the ozone in the atmosphere that we're living in, called the troposphere, is considered a pollutant. In the presence of UV radiation, molecular oxygen is being bombarded with the atomic oxygen to create ozone. When the radiation disappears, the ozone decays back. The ozone is being used to generate back molecular oxygen. And notice now when the UV radiation disappears, let's say it's dusk or nighttime, when there is no more sunlight coming out, the sun goes away, the energy goes away, we start back to where we came from. In the morning when the sun goes up, the UV radiation from the sun starts this cycle. At night when the sun goes down, we generate back molecular oxygen and we're ready to begin the next day. So ozone works in conjunction with molecular oxygen to prevent radiation. I was trying to write prevent radiation from ever hitting the troposphere and keeps it up in the stratosphere. The Chapman cycle, I would say, isn't critical to memorize, but it's more of a process of understanding. We need the sunlight to initiate this cycle. When the UV light from the sun hits molecular oxygen, it breaks the double bond. Those oxygen atoms go now into the cycle that feeds the production of ozone. Now the ozone regenerates back and forth. As long as we have energy available from the sun, this process will continue and continue. Until the sun goes down, the ozone regenerates into molecular oxygen. Take away the source of energy and the cycle will stop. You'll be asked to place those in your sapling assignment. Ozone creation. So this is called the Chapman cycle. Arrange the reactions in order according to the cycle. So with this visual aid, you should certainly be able to do that. What's the very first reaction you see? That's diatomic oxygen breaking into atoms of oxygen. That's diatomic oxygen breaking into two atoms. This is the abbreviation H-nu. Remember, that's energy. So in the process of hitting it with energy, that's this, we break apart molecular oxygen into atoms. What comes next? The oxygen atom collides with molecular oxygen to build ozone. We see the production of ozone in our second step. And when the light goes away, the ozone regenerates to molecular oxygen and the cycle can start all over. If you see H-nu, this is Planck's constant. This is frequency. So instead of writing energy, they're writing its equivalent, H-nu. That's a packet of energy from the sun. And as we kind of wrap up our lesson, we're looking at biological effects of UV radiation, skin cancer, of course, being the most prevalent. Overexposure to sunlight is one of the leading causes of skin cancer. They may develop many years after repeated excessive exposure, even after it stopped. The UVB spectrum of sunlight is the culprit, more so than UVA, which is very low energy. So UVB protection is important, especially in your sunscreens. And you're looking at all different varieties of skin cancers depending on the skin cells that are affected. There are indeed fatal melanomas, but most skin cells can be treated by simple removal. So you're looking really at UVB UVB radiation protection when you're looking at your sunscreen. And the rest of these are processing questions related to your sapling, looking at how UVA, UVB, and UVC affect skin cancer. We know UVB is greater energy than A, resulting in more damage to DNA molecules. There's your sapling here. There's just processing questions related to those things we've been talking about. The other topic mentioned kind of near the end, and when you're outlining, you can look at radicals. Another byproduct of radiation are radicals. Notice these electron dots. H has a dot after it and O has a dot after it. When I see that they have an unpaired electron, they are defined as a radical. A radical is a molecule with an unpaired electron. Now what's different about a radical, it's not a charged atom, but an unpaired atom makes them very highly unstable, very reactive, and thus they're going to work to destroy the ozone as well. So for instance, dinitrogen monoxide produces a radical. NO is a radical. And about certain UV radiation will cause the molecule to break apart. So the two ends separate from the O and we come up with a radical. And this was going on in the 1970s. This is just reading from your text. One of the reasons we stopped researching supersonic transports is we were actually depleting the ozone at a very, very high rate to the fuel that was being used to supply the engines for this particular research. So a radical. We have nitrogen dioxide, nitrogen who lives in group 5A with its 5 valence electrons. Oxygen lives in group 6A, and I see that there are 6 of them, 6 dots altogether. So in a molecule of NO2, I have 12 plus 5, I have 17 electrons that I'm allowed to place. So if I place N in the center and I attach an oxygen both back to it, by creating this site of attachment, I had 17. I just used 4, 1, 2, 3, 4 to make those single bonds. I'll fill out the octet of the outer elements. And by doing that, I used 12 electrons, leaving me just 1 more. That extra electron will get placed on the nitrogen. Now I can arrange a double bond here to get nitrogen up to at least 7 electrons. So I'll erase a couple of dots from oxygen and place a double bond. So oxygen still has 8, 2, 4, 6, 7 on the nitrogen, and this oxygen still has 8. This is a radical of N2O because it has an odd number on the nitrogen. Now you could have placed the double O in either direction. It exhibits resonance. And the same will happen when you draw for NO. We'd have 11 dots to place. 5 from this nitrogen, 6 more from that oxygen makes 11 dots. When I connect them together, I place 2 electrons to connect them as a shared pair. I'll finish the octet on the oxygen, and that uses 6 more electrons, so that leaves me a remainder of 3. So I can place them 1, and then what I want to do is 2, 3. I have no electrons left, but what I'll end up doing here is making some bonds to get nitrogen the number of electrons at least as close to 8 as I can. 2, 4, 5, 6, 7. There is the electron dot structure for NO. A radical, because I have an odd number of electrons, a very unstable, highly reactive situation. And there's the answer. I just drew that with you. So these radicals go to work destroying the ozone. Another culprit of destroying the ozone are chlorofluorocarbons, commonly called CFCs. You'll hear them trichlorofluoromethane. So I'll just try that. Trichloro means there's 3 chlorines. Trichloro, fluoro, that's the element fluorine, methane, that's freon. Another molecule is called dichloro, 2 chlorines, trifluoro, 2 fluorines, methane is that carbon in the center, and that's Freon 12. CFCs are not naturally occurring molecules. They are synthetic. They're made for a variety of uses, but they are very unstable in terms of reacting with ozone and cause the depletion of the layer. Up in the stratosphere, in the ozone layer, they'll convert ozone into atomic oxygen. So free radicals such as OH, again, an odd number of electrons, or NO, a radical, cause the depletion but are naturally occurring. CFCs are not naturally occurring. So in nature, there are certain things that deplete the ozone, and we as humans have created certain compounds that have destroyed the ozone. So what we're looking at here is that Freon 1 or Freon 11, Freon 12, those molecules we just drew, and we're looking at how the UV radiation breaks apart a carbon-halogen bond. And when it does so, it breaks apart a carbon-halogen bond, it creates a radical, and that radical destroys the ozone layer. And this chemistry is probably just interesting at this point. I wouldn't say it's mandatory learning, but a radical reacts with ozone in a process, kind of a cyclic process, where the radicals are free to attack more and more and more oxygen. It's the chlorine radical that actually acts as a catalyst in this particular reaction. A catalyst is something that speeds up a chemical change. So through the process of this chemistry, and the slide kind of didn't end up just right when I converted it from PowerPoint to Smart, we're looking at this radical destroying ozone is the overall effect. And so just a little graph here as we wrap this lesson up. In the stratosphere, where ozone is of high concentration, in the stratosphere where chlorine is of low concentration, if I don't have the radicals in the stratosphere, I have lots of ozone. But if I have an increased concentration of radicals, such as chlorine from CFCs or NO from fuels and emissions of pollutants, if the pollutant increases, the ozone depletes. More pollutant, less ozone. And those are the last final thoughts here on our sapling and in the lessons. Chlorofluorocarbons are pollutants that persist in the stratosphere when they have been implicated in the depletion of ozone layer. This particular question is asking us to look at this dot structure and just write its chemical formula. So I see that there's carbons, chlorines, and fluorines. Now I wrote them just by kind of glancing at what I saw first. I see that in the center there's 2 carbons. I see 1, 2, 3 chlorines, and I see 1, 2, 3 fluorines. Now chlorofluorocarbons, you might think chlorofluorocarbon, but it absolutely doesn't matter the order of which you write those, just that you have the subscript associated with the element correctly. But the formula, the order of those elements, it'll take any direction. How many valence electrons in this whole molecule? How many electrons do we see? And I know each bond counts for 2 or a shared pair, but I might suggest an easier way. I know carbon lives in group 4A, and there's 2 of them, so I know that each carbon is going to donate 4 electrons for a total of 8. This is its group number telling me the valence electron. Here's chlorine. Chlorine lives in group 7A. It would have 7 valence electrons, and I see 3 of them. That's a total of 21. And the same for the fluorine. It also lives in group 7A for a total of 21. So here we have 21 and 21 is 42. 8 more is, carry my 1, that's 50 valence electrons. I could count all the dots, and each line represents a shared pair. I bet we get 50 in either direction. The rest of my presentation are sapling questions. Draw the Lewis dot structures for carbon CFC11, CFC12, and CFC22, and they're giving us the formulas down below. So the Lewis dot for CCl3F, we know to place the carbon in the center. We'll have 3 chlorines around, and you'll have to put dots around all those chlorines to get this right on your sapling. And the other one here is a single fluorine, and you'll see that attached in this arrange. If I want to draw CFC12, I have 2 chlorines and 2 fluorines. And if I want to draw CFC carbon 22, there's 1 chlorine, 1 iodine, and 1 fluorine. Now that might be hard to see, but there's still 4 attachments. One of those, oh, that's not iodine, that's Cl. So that's CH, I apologize, I don't have my glasses on. C is attached to an H, also attached to a chlorine, that's a Cl, and then 2 fluorines. And don't forget, these would all have 2 dots around each side, completing their octet. Not the hydrogen, it only needed to have 2. And again, this carbon would have 2 chlorines, 2 fluorines. It doesn't matter the sides that you select, fill the octets around each of those halogens to complete the Lewis structure. We just drew a CFC in 3 different arrangements. I'm going to end our podcast here tonight. Thank you for listening. I hope we took some good notes together, and I'll see you again.